We start looking at some examples similar to the polarity. So the first example I'm going to do is hybrid for BCl2 hybrid. So we have to draw the Lewis structure, and I hope you remember the Lewis structure. The Lewis structure is BeCl, Cl, and then this is the lone pair. So first we predict the number of sigma bond in the structure. So there is 2 sigma here, and there is no lone pair on the central atom. That means the sigma plus lone pair, 2 sigma plus 0 lone pair, 2 central atom will undergo hybrid sp. That's the first step we do. The second step is we have to write the beryllium ground state electronic configuration. Normally we can write valence shell configuration for the longer electronic configuration, meaning to say beyond period 4 and 5 you can use the valence. If period 2 and 3 you write the complete one, but again the focus is only on the valence. For example, for beryllium, which is 3 proton number, sorry, not 3, 4, sorry, beryllium is 4. So when I write the electronic configuration, 1s2, 2s2, okay. So we only focus on the valence only. So the ground state configuration, I can write here. I have to draw the orbital diagram, not write it. Draw the orbital diagram. So I have 2s, okay, and we have 2 electrons here, okay. The second step, we have to write beryllium excited state. Sorry, beryllium. We have to write here excited state. Please take note, our beryllium should have a p orbital when we do the hybridization. That means here we have empty 2p orbital. So what will happen? What will happen at excited state? One electron from 2s will move to 2p, will be promoted to 2p. This is called excited state. Next is beryllium hybrid state. In hybrid state, we will mix the s orbital and the p orbital. So we will get 2 boxes known as sp hybrid. S will have 1 electron, p will have 1 electron, but they are not called sp now. They are considered as hybrid orbitals of sp. Okay. The next information that we should know, what is the geometry of sp? Each orbital has their own geometry. For sp, the geometry is called linear. Okay, so now we go to the drawing. Before we move to the drawing, do not forget about this atom. Do not forget about this atom, which is our terminal atom. So we write their configuration as well. So chlorine ground state, one S2, 2s2, 2p6, 3s2, 3p5. So we check the valence configuration and you look at the 3p, 1, 2, 3, 4, 5. So students can observe there is an unpaired electron at the last orbital, the last box. This unpaired orbital will be used for the sigma bonding with the central atom beryllium. So now we can get a drawing. So beryllium at the center And what is the what is the geometry? Is linear. SP is linear. So we draw a linear, okay? And then do not forget to label the leaf as SP. It's a linear. We must draw in the linear format. Now, how about this one? For chlorine, for chlorine, the 3p orbital, which has the unpaired electron, the p orbital, the shape is dumbbell. So we draw one dumbbell here. This is for chlorine atom on the left. We draw a dumbbell here. Sorry. Sorry. Okay. Chlorine here. This is on the right hand side. So we have left hand side one chlorine, right hand side one chlorine. Both will have the same valence configuration. So each of the chlorine will have one unpaired electron. So you place the unpaired electron here on the box where there is overlapping. Before that, we put the beryllium. You can see here, beryllium has two electrons, right? So one I place here, the other one I place here. And then from the chlorine, which I told you just now, from the chlorine here, this one, we place here one, and we place another one here. One belong to the left, one belong to the right. So what we can conclude here? There is overlapping here, shows a sigma bond. Overlapping here shows the sigma bond. This is hybridization of beryllium chloride.